Today we are going to discuss the concept of connectivity and related to the graph theory. It is important in various domains, like when we are talking about the reliability of some networks, we are checking that how strongly a transportation route is connected. Uh, so these are few of the applications where we can use the concept of connectivity. Many more are there. Let us try to discuss the concept. So when we are talking about the connectivity inside the graph, the first thing that we should know is that what exactly we mean by a connected graph. So a graph is said to be connected if there exists a path between every pair of vertices. Between every pair of different vertices, better to say. A graph that is not connected is called as a disconnected graph. Here in this definition, we can say one more definition is included, which is path. Now, what is a path? As like a path, as it is a general terminology, we can say path is any alternating sequence of vertices and edges. Any alternate sequence, like a path can be from V1 using E1, then moving to V2 using E2, moving to V3. This may be one of the path which is covering from the vertex V1 to V3 by using the edges E1 and E2. Okay, the definition of the connected graph is saying between every pair of vertices a path exists. For example, if I'm talking about the graph 1, let the name of these vertices is A, B, C and D. Now you can observe from here, we can move from A to anywhere, whether it is B, C or D. If I want to move to C, it can be done thoroughly directly by using this edge. I can call it as E1. So A, E1, C. This is one of the path which is covering from vertex A to C. We can cover another path from A to C, which is let it be A if this edge is E2, A, E2B, B, E3C. So this can be written as A by using E2, B by using E3C. Another path. So, if between every pair of vertices at least one path exists, such graph we call as a connected graph. These are few of the example of connected graph. If in the second graph I add something, let it be this is vertex A, this is vertex B, this is C and this is D. Let us add one more vertex E and this is F, and let us connect them by using some of the edges. So now this whole graph called as a disconnected graph, because we can't move from the vertex A to the vertex F. We can't move from the vertex D to vertex E. So here we are having some pair of vertices, between them path does not exist. So we call this graph as disconnected graph. The last example is also for the connected graph. From anywhere, we can move anywhere. Means if I take vertex A, I can move from vertex A to B, A to C, A to D. Okay, this is what we mean by a connected graph. Now, in connectivity, there are four major points that we are having. The first point, we call it as a cut edge. The second point, we call it as a cut vertex. The third one is vertex connectivity, and the last one is edge connectivity. Now, let us try to understand these definitions one by one. So, the first one is cut vertex or cut point. So, basically, cut vertex or cut point is a single vertex. It is a single vertex whose removal from the graph make the graph disconnected. If there are some vertex, better to say specifically one vertex, when we remove this vertex from the graph, it will become disconnected. Then that vertex we call as a cut vertex. The same manner when we talk about cut edge, the removal of a single edge, the removal of a single edge which make the graph disconnected is called as a cut edge. Disconnected means what? You are able to find one pair of vertex. Between them, a path does not exist. So as we can see, this graph is a connected graph. Connected means from anywhere we can move anywhere. So we call it as connected. Now, if in this graph I remove this vertex C, I remove this vertex C, then how the shape will looks like? This is the shape. The shape of the graph will looks like this will be A, this is B, and this is vertex D. The center we remove C. So now this part is your vertex E. Then over here F. Then here I am having G, and somewhere here we are having vertex H. Somewhere here we are having vertex H. So now if you see, and let me draw it again. Yes, so this is your vertex, the bottom one H. You can see now this is a disconnected graph. We can't move from the vertex to vertex E. We can't move from vertex D to vertex F. So comes out disconnected graph. So we can say the cut vertex of this graph is vertex C. And this is how it will be written. In place of C, we can also remove the vertex E, then the graph will also becomes disconnected. So either C or E. Except these two, there is no other vertex whose removal makes the graph disconnected. So these two are the only vertex which makes the graph disconnected. So we call them as a cut vertex. Remember, it is always a single vertex. So in one time, we are removing only one vertex. Okay, so this is we called as a cut vertex or cut points. On the same side, if we are talking about cut edge, so in cut edge, in place of vertex, we are interested to remove an edge, exactly one edge, better to say, whose removal makes the graph disconnected. So if from this graph I remove this edge E, CE, then the graph will looks like this. Then the graph is separated into two sections or two disjoint part. Now you can see if I put the name which is A, B, C and D, this is your E, F, G and H. We can't move from the vertex C to F. We can't move from vertex A to E. Once again disconnected. So the cut edge of this graph is C, comma E. This is how we can write. If the name is there, let it be even. We can say even is the cut edge of the graph. One point that here we are supposed to take care, when we are removing an edge from the graph, then only that edge removed from the graph. But on the same time, when we are removing a vertex from the graph, then all the edges which is connected to this vertex will also get out from the graph. As like over here, when I remove the vertex C, you can see all the edges which is connected to the vertex C are removed from the graph. Okay, so this is how we can see that what is cut edge and cut vertex. Now over here we can see this is the cut edge for the graph. This is the cut edge for the graph. This graph do not have any cut edge. This graph do not have any cut vertex, because removal of a single vertex or single edge is not making this graph disconnected. Now the extension of the cut edge and cut vertex is the connectivity. One is known as the edge connectivity and one is known as the vertex connectivity. Now, if we are talking about vertex connectivity, so what it says, vertex connectivity is the minimum number. Pay attention for it. Minimum number of vertices whose removal from the graph makes the graph disconnected or reduce it into single vertex graph. Single vertex graph. So one point added in the definition. Either the graphs comes out disconnected or reduced into a single vertex graph. Okay. So if cut vertex exists, vertex connectivity will be 1, because in that case minimum one vertex need to be removed to make the graph disconnected. Okay. Now if vertex connectivity does not exist, then in that case if cut vertex does not exist, then in that case vertex connectivity will be at least 2, or we can say 2 or more than any number. Similarly, the edge connectivity gives you the minimum number of edges whose removal from the graph makes the graph disconnected. Minimum number of edges. If you just paying attention, it is every time we are talking connected to disconnected, disconnected to connected, like scenarios. Okay. So minimum number of edges whose removal from the graph makes the graph disconnected, we call it as a edge connectivity. Let us see some examples. So this example, if you see the first example, it do not have any cut vertex. It do not have any cut edge. Cut edge does not exist for this graph. Cut vertex does not exist for the graph. Why? Because if I remove a single edge, the graph is still not disconnected. It will connect it once again. If I remove any single vertex, it is not disconnected. Now, in place of cut edge, if I am talking about vertex connectivity. So see, if I remove this edge, the graph is separated into two disjoint parts. So disconnected graph. So edge connectivity for the graph will be 2 because we are removing two edges from here. In the same manner, vertex connectivity, if I remove vertex A and vertex J, if I remove vertex A and J, then this vertex I will comes out disconnected from the leftover part. So vertex connectivity of this graph is also 2. Okay, do remember we are supposed to find the minimum number of edges and minimum number of vertices. It's not like in this graph I am removing any number of edges or vertices. Yes, it should be minimum always. For this graph, the cut edge is E9. E9 is the cut edge. So what will be the edge connectivity? Yes, it is 1. Removing one edge, making the graph disconnected. If I am talking about vertex connectivity, so how many minimum vertex should be removed? If you remove this vertex from the graph, so all the edges connected to it also get removed from it. So this vertex, if I put the name of this as A, this vertex A will become disconnected from the leftover part. So the graph will become disconnected. So the vertex connectivity is also 1. Another major difference is what? Cut vertex and cut edge is the name of the vertex, and on the other side, cut edge connectivity and vertex connectivity is always a number. Now let us try to find cut edge, cut vertex, edge connectivity, and vertex connectivity for some general graphs. So suppose if I am talking about the complete graph Kn. I'm talking about complete graph Kn. So a complete graph Kn is a graph. What is complete graph? A graph in which between every pair of vertices, exactly one path exists. So this is a graph ABC. The name will be K3, having vertex between every pair of vertex. If I try to draw K4, so four vertices graph, where between every pair of vertices there exists one edge. The same manner if I draw K5, so this is how K5 looks like. 5 vertices A, B, C, D, E. Just connect every other vertex to the rest of vertices. This will become K5. So K5, K4. Okay, so if you see the first one, is there any cut edge in this graph? Cut edge, you can see does not exist. Removal of single edge, not making the graph disconnected. Now, cut edge is not there. Cut vertex, it is also not there. Talking about edge connectivity. So if you remove these two edges, the graph will become disconnected. Vertex connectivity. The second definition that I added, if you remember, if you remember, either disconnected or left the graph into a single vertex graph. If you remove C, A and B is still connected. If you remove B, now the graph left over with a single vertex. So I remove the two vertex. The same manner, try to find the cut edge, cut vertices for other graph, which is K4 and K5. Okay, so this is all about the connectivity of the graph, like or how to find it for the different graph. In the next class, we will try to find cut edge, cut vertices, edge connectivity, vertex connectivity for some special types of graph. I hope you understand it. Now closing the session. Thank you.